are in Statistical Rethinking, Chapter 9, I guess second edition of Statistical Rethinking. And this chapter is all about Markov chain Monte Carlo. So just a little bit of background. So to this point, all of the models that we have been using or trying to work with, we've worked with the QAP function in Statistical Rethinking, which is just an optimization method, but without going too far into what it's doing. But what that method kind of relies on is that the posterior distribution can be kind of approximated with normal distributions, roughly. I'm not saying that very well, but anyway, when we start to get into probability distributions that are not, where there are not good normal approximations, we have to use something else. And so what we use, well, what the Rethinking package uses is Stan, and what Stan uses is a method called Markov chain Monte Carlo, and specifically it uses a variant of that called the Hamiltonian Monte Carlo, and more specifically than that, it has kind of it applies some neat tricks to it, and so it's called the no U-turns sampler. Okay, none of that will be covered in this book or any further in this series of videos, but that's just some context. Okay, so so there are several ways of using Markov chains, and one of the, I think maybe the first way that was developed was called the Metropolis algorithm. Okay, and so that's what this first question here, 9E1, deals with. Okay, so now the book kind of gives a cute little example about Markov chain, or about the Metropolis algorithm. And it's fine, and I don't know that you really need to know the ins and outs of the Metropolis algorithm to be able to do Bayesian inference, especially since the software that you'll be using is not doing Metropolis. But understanding how the Metropolis algorithm works kind of starts to give you bearings for how some of the more complicated algorithms work. And some knowledge of the more complicated algorithms can be useful as your because you will encounter errors when you are running those models. And if you kind of have a sense of how those are working, then you can troubleshoot a little bit more effectively. Okay, that's a lot of throat clearing. So, okay, so question 1 is, which of the following is a requirement for the simple Metropolis algorithm? And then it gives 3 things here. And so we'll go through these one at a time. But I thought that I might give my own version of the Metropolis algorithm, just so that you've seen it in a couple of different ways. And then I would also refer you to A Student's Guide to Bayesian Statistics by Ben Lambert. It's a very good book. It's maybe a little bit more nuts and bolts than Statistical Rethinking, but still very approachable. And it has some very approachable explanations as to how some of these algorithms work. Okay. So here's my version of Metropolis algorithm. So we imagine a space of parameter values, theta. Okay, and so theta could represent one parameter, it could represent many parameters. Okay, and so we imagine a space where these potential values sit. Okay, and but for our demonstration here, we'll just imagine one theta, one parameter, and that means that its space of values is just a line, just like here, like I have in this figure here. Okay. So now the posterior distribution sits in this space, right? And so so the posterior is represented here by this blue line, so it has a particular probability for any given value of theta. Okay. So the posterior sits here in our distribution space. Okay, and so more probable values, of course, have a greater amplitude on the y-axis, or our posterior axis, our probability axis. Okay, so now what we want to do is to be able to estimate or calculate this curve here. Okay, But sometimes this curve cannot be computed analytically. Right? We can't sit down with pen and paper and then start to do calculus and arrive at this curve. It's too complicated, right? And so we have to approximate it, and so we have to approximate it with numerical methods, and that's what the Metropolis algorithm is. Okay? And so what we do in the Metropolis algorithm is we propose some theta value, okay? And then we calculate the likelihood times the prior for that particular theta value, right? So we pick a theta value, and then we put in we calculate this, okay? Now this expression, the likelihood times the prior, is just the numerator of Bayes' theorem, okay? And so so the value that we're going to calculate is proportional. It's not equal to, but it's proportional to the posterior, all right? Now, because this needs a name, I'm not going to call it the numerator, or I might, but I'm going to call it the weighted likelihood. I don't think it goes by that name, but I'm going to call it the weighted likelihood because it's the likelihood weighted by the prior. So if I say weighted likelihood, that's what I'm referring to. And again, the weighted likelihood is proportional to the posterior distribution. Okay? So we start by just proposing a random theta and calculating its weighted likelihood. Okay? And then we propose another potential value for theta, and then look at its weighted likelihood. Okay? So now if the suggested value for theta, which I'm calling ST1 here, if the suggested value has a greater probability, or I'm sorry, a greater weighted likelihood than the current value, then we accept this new proposal. So in this case we accept ST1. Okay? But it could be that the suggested value is smaller, or the probability, or I'm sorry, the weighted likelihood of the proposed theta value is smaller than the current one. Now, in this case, we don't automatically accept or reject the new suggested one, okay? But instead, we accept the new one with the probability of the ratio of their weighted likelihoods. Okay, so I apologize for speaking through this. I hope that you go to the Colab sheet and actually read this to make more sense. Hopefully I'm just kind of walking through what you could be reading. But anyway, so we repeat that process many, many times, making new proposals. And every time we make a proposal, we accept or reject it based on the rule that we just laid out. Okay, and whenever we're accepting one, we can keep track of that. We can tally it. And then over many, 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 many samples, we can represent all of those samples and their frequency as a histogram. And as we collect more and more samples, that histogram will begin to approximate the shape of that posterior distribution. Okay, that's roughly the Metropolis algorithm. Okay, so now let's go through the actual question, which is we have to identify which, if any of these, are requirements for the Metropolis algorithm. Okay, so the first one is the parameters must be discrete. Okay, so now in the book, the example that's given is kind of this king, and he's jumping from island to island or something. And so each island represents a parameter value, and those parameter values, being islands, are discrete. But that is not that's not required. Okay, so all that's required is that from any point on the posterior distribution, or proposals of the theta values, we can propose other values. And so it does not matter whether or not theta is continuous or discrete. Okay, so that's not required. Okay, second, the likelihood function must be Gaussian, or a normal distribution. Okay, so in other words, the likelihood. So again, this is not required. Okay, so the Metropolis algorithm really is computing this guy right here, and this is a completely generic form. It does not matter. It does not matter how p data given theta is distributed. Okay, it accepts this form in whatever distribution the data happens to come in. Okay. Okay. Finally, part 3, or question, or possible requirement 3. The proposal distribution must be symmetric. Okay, so this one is required, but it will require it to explain why it's required will itself require a little bit of explanation. Okay. So first, what is meant by a symmetric proposal distribution? Well, basically it means if I'm at one theta value and I propose a second theta value, the probability of having proposed that second theta value has to be equal to the probability of being at the second theta value and having proposed the first. Okay, so I hope that makes sense. Okay. So that's the first thing to be clear about. And then the second thing to be clear about is that just because the proposal distribution is symmetric, going from A to B or B to A, that does not mean that the acceptance is symmetric, right? Again, the acceptance is based on, the estimation or the calculation of the weighted likelihoods, and then using the accept reject rule that we already went through. So one very quick way we could explain why the proposal distribution needs to be symmetric could be something like, so as we're generating our approximated posterior distribution, we are already filtering samples based on our accept reject rule. And so to further sample it by biasing which, by not having an equal distribution or proposal distribution, what that additional filtering would bias our Markov chain as we're building up these samples, and so it could bias it away from actually approximating the true posterior distribution, right? And so we don't want that. Okay, so that's kind of a hand-wavy explanation. And so if you want a more technical explanation, then we need to go deeper. Okay, and so that's what's happening here. Okay. So let me go through this here. So the idea of using a Markov chain to approximate our true posterior distribution is like this. So imagine that we have our true posterior distribution, and we take a sample of theta values from there. Okay, so we would have this set of sampled theta values from the posterior distribution. Okay. The idea behind our Markov chain and trying to use a Markov chain to approximate our posterior distribution is really to say that we want our Markov chain to propose values of t, where t is like our estimated theta, okay, where the probability of those t's is equal to the probability of the sequence of theta values that were sampled from the actual posterior distribution. Okay, so in the end, right, what we want is that the joint probability distribution of the samples our Markov chain generates, we want that probability distribution to approach the probability distribution of the samples we drew from the actual posterior distribution. Okay, so we need several samples to do this, many. So as n gets very large, our Markov chain, or the joint probability of our Markov chain, should approximate the joint probability of our posterior samples. Okay. Now, importantly, once that convergence is, has happened, or it's very close, we don't want our Markov chain distribution to start to drift away from the posterior distribution. Okay, and the only way to ensure that is to make sure that the proposal distribution is symmetric. And so in order to, for you to be able to take my word on that, we need to demonstrate that. Okay, so say that we have two, so we're going to consider two values, theta A, or TA, and TB. Okay, and because we've done a good job of designing our chain with the appropriate accept reject rule, these are, the probability of having drawn TA is distributed according to the actual posterior probability for both of these. Okay, and we're going to stipulate that the probability of TB is greater than the probability of TA. So let's imagine one scenario where we start at TA and then propose TB. Okay, and we do so with the probability of suggesting TB from the point of TA. Okay. Well, now in this scenario, because the probability of TB is greater than the probability of TA, we always accept this. Okay. So in other words, the set TA-TB is distributed as the joint probability of TA-TB, okay, and that is equal to the probability of having been at A, TA, times the probability of suggesting B from A. Okay, right? So that's our joint probability distribution. Okay. So now we're going to imagine a parallel universe where instead of starting at TA, we start at TB and propose TA. Okay, so we start at TB and we propose TA with a probability of proposing TA given TB. Okay. Now, since the probability of TB is greater than the probability of TA, we don't automatically accept TA. Okay, but instead we accept or reject it based on the rule that we've already went through, the ratio of the weighted likelihoods. Okay. So now in this universe, again, where we started with TB and proposed TA, right, we now have this set of, we have this posterior distribution, the probability of T and probability of A, is equal to the probability of having started at TB, then proposing A, TA, times the probability of actually, well, this ratio, which is a probability of accepting A from B. Okay. Well, now, so this is our expression. Okay. And so this term and this denominator here are the same and they cancel out. So that means that in this second universe, our joint probability distribution is equal to this. Okay. All right. Now, finally, for the final step here, so if both of these, whether we start at A or at B, we will arrive with the appropriate accept-reject rule at the posterior distribution. And there's only one posterior distribution. And so that means that this joint probability distribution and this joint probability distribution need to equal one another, right? They need to be equal. Okay? And so so if I just expand those, that means that the first joint probability distribution in the expanded form must equal the second probability distribution in the expanded form. And notice that they both have PTA here, as well as, but they have different proposal distributions, right? One starts at TB and one starts at TA. Or I'm sorry, one starts at TA, one starts at TB, okay? But if these two sides are equal, that means that this term and this term must be equal, okay? So in other words, the proposal distribution from A must equal the proposal distribution from B in order to arrive and stay at the posterior distribution. Okay, so I know that one probably got a little bit too technical, but go through, read the Colab sheet, check out Ben Lambert's book, and there's more technical resources beyond that, but hopefully that might have lent a little bit of insight into how this is working.